Imagine a world where reality itself behaves in ways that defy our intuition. A world where particles can exist in multiple states at once, where information seems to travel faster than light, and where certainty is replaced by probability. This is the quantum world, a realm that challenged even the greatest mind of the 20th century, Albert Einstein. Although he revolutionized physics with his theory of relativity, when it came to the emerging field of quantum mechanics, he found himself in a profound dilemma. To truly appreciate the profound nature of quantum mechanics, we must first understand the world as classical physics describes it. A world that, for centuries, seemed predictable, orderly, and logical. Classical physics, the framework developed by luminaries such as Isaac Newton, Galileo Galilei, and James Clerk Maxwell, portrayed a universe governed by clear laws. Objects had definite positions and velocities. The trajectory of a projectile could be calculated with precision. Planets moved through space following predictable paths. In this classical world, the universe was like a giant clockwork machine. If you knew the positions and velocities of every particle, you could, in principle, predict everything about the future. This deterministic vision provided comfort to generations of scientists, engineers, and thinkers. Yet, at the turn of the 20th century, a series of puzzling experimental results began to challenge this orderly view of reality. Phenomena such as blackbody radiation, the photoelectric effect, and the behavior of electrons in atoms could not be explained by classical laws. Light, for instance, had long been understood as a wave, yet experiments revealed it also behaved like a particle. Similarly, electrons orbiting an atomic nucleus did not spiral inward as classical physics predicted, but instead occupied discrete energy levels. These anomalies pointed to a new layer of reality, a microscopic world where the rules of classical physics no longer applied. This world would come to be described as quantum mechanics. Quantum mechanics, in its essence, introduced a fundamental shift in how we perceive reality. Unlike the deterministic predictions of classical physics, quantum theory proposed that at the smallest scales, nature is intrinsically probabilistic. Instead of being able to determine with absolute certainty the outcome of every event, we are limited to calculating probabilities. For example, while classical physics could predict the exact path of a thrown ball, quantum mechanics can only tell us the likelihood of finding an electron in a particular region around an atomic nucleus. This is not a limitation of our measurement tools. It is a reflection of nature itself. The universe, at its most fundamental level, is governed by probability, not certainty. To illustrate this, consider the famous double-slit experiment, a cornerstone demonstration in quantum mechanics. In this experiment, a beam of particles, such as electrons or photons, is directed at a barrier with two slits. If one slit is open, particles form a pattern on a screen behind the barrier as expected. Classical intuition would suggest that if both slits are open, the particles would simply form two overlapping patterns corresponding to the two slits. Yet the results are far stranger. When both slits are open, an interference pattern emerges, indicating that each particle behaves as though it passes through both slits simultaneously, interfering with itself like a wave. Even more astonishing, when detectors are placed to observe which slit each particle passes through, the interference pattern disappears, and the particles behave like classical particles again. This experiment defies classical logic and vividly demonstrates the dual wave, particle nature of matter, a phenomenon with no parallel in everyday experience. The probabilistic nature of quantum mechanics also manifests in the concept of superposition. In this framework, particles do not have a single, well-defined state until measured. Instead, they exist in a combination of all possible states simultaneously. This principle is famously illustrated by Schrödinger's thought experiment involving a cat in a sealed box. The cat's fate, alive or dead, is linked to the state of a quantum particle. According to quantum theory, until the box is opened and an observation is made, the cat exists in a superposition of being both alive and dead. While this may sound absurd when applied to macroscopic objects, it captures the counterintuitive truth of quantum behavior at microscopic scales. Reality is not fixed until it is observed. These principles of superposition and probabilistic outcomes challenge our deeply ingrained classical intuition. In everyday life, objects have definite properties that we can observe without fundamentally altering their state. If you look at a chair, it is either there or it is not. It does not exist in multiple positions simultaneously. Quantum mechanics, however, suggests that at the level of particles, such determinacy does not exist until measurement occurs. The act of observation itself plays an active role in defining the state of a system, a concept that has led to debates about the role of consciousness in physics and the nature of reality itself. One of the most striking implications of quantum mechanics is the idea that certainty is replaced by probability in the prediction of outcomes. Heisenberg's uncertainty principle formalized this concept, stating that certain pairs of properties, such as position and momentum, cannot both be precisely measured simultaneously. The more accurately one property is known, the less accurately the other can be determined. This is not due to experimental flaws, but is a fundamental characteristic of nature. At the quantum level, uncertainty is inherent, and the universe cannot be fully predicted in the deterministic manner classical physics suggested. This principle revolutionized our understanding of the limits of knowledge and challenged the notion of an entirely predictable universe. The probabilistic nature of quantum mechanics extends beyond the micro world into the fundamental building blocks of matter. For instance, the decay of radioactive nuclei is entirely unpredictable for any individual atom. Physicists can calculate the half-life of a large collection of atoms with remarkable accuracy, predicting that half will decay within a certain period, but they cannot determine when a specific nucleus will decay. This intrinsic randomness is not due to hidden information or imperfections in measurement. It is a fundamental property of nature. Einstein found this deeply troubling as it challenged his belief in an ordered, predictable cosmos, and he famously expressed his discomfort with the phrase, "God does not play dice with the universe." Yet, despite its counterintuitive implications, quantum mechanics has proven extraordinarily successful. The probabilistic framework allows scientists to make precise predictions for experiments and technologies that have transformed the modern world. Semiconductors, lasers, and magnetic resonance imaging, all foundational to contemporary life, depend on principles derived from quantum theory. Quantum mechanics has enabled the development of technologies that harness the probabilistic nature of particles, showing that even a universe governed by chance can be remarkably predictable when probabilities are aggregated across many events. Another illustration of quantum mechanics' defiance of classical intuition comes from quantum entanglement. When two particles become entangled, their properties are linked in such a way that measuring one immediately influences the state of the other, regardless of the distance separating them. This phenomenon, which Einstein referred to as spooky action at a distance, challenges the classical notion of locality, the idea that objects are only influenced by their immediate surroundings. Entanglement has been experimentally verified countless times and forms the basis for emerging technologies such as quantum cryptography and quantum computing. Here again, the universe behaves in ways that defy our everyday expectations, revealing a reality far stranger than classical physics could ever predict. Quantum mechanics also challenges our understanding of causality and the flow of information. In classical physics, events follow a clear cause and effect relationship. Every effect has a specific cause, and information cannot travel faster than the speed of light. Quantum phenomena, however, suggest that correlations can exist instantaneously between entangled particles, implying a form of connection that transcends classical space and time. While this does not violate the theory of relativity, because no usable information travels faster than light, it underscores the ways in which quantum mechanics forces us to rethink foundational concepts that seemed unassailable just a century ago. Moreover, the probabilistic nature of quantum mechanics has philosophical implications that extend beyond physics. It forces us to reconsider the nature of reality, the limits of human knowledge, and the relationship between observer and observed. The universe, as revealed by quantum theory, is not a static, deterministic machine, but a dynamic, probabilistic tapestry in which certainty emerges only through interaction and observation. This perspective has inspired thinkers across disciplines from philosophy to computer science to explore new ways of understanding the interplay between knowledge, reality, and measurement. In education and research, teaching quantum mechanics often requires unlearning intuitive notions inherited from classical experience. Students and researchers must grapple with a reality where familiar concepts like position, momentum, and even existence are not absolute but probabilistic. This mental shift is essential for exploring phenomena at atomic and subatomic scales. Without embracing the inherent strangeness and uncertainty of quantum mechanics, one cannot fully grasp the depth of its insights or the power of its predictive capabilities. As quantum mechanics continued to develop, physicists began to realize that its probabilistic nature was not merely a mathematical convenience, but a deep feature of reality itself. Unlike classical uncertainty, which arises from incomplete information, quantum uncertainty exists even when everything that can possibly be known is known. This distinction is crucial. In classical physics, if we do not know the exact position or speed of an object, it is assumed that these quantities still exist precisely. We simply lack the means to measure them. Quantum mechanics, however, asserts something far more radical. Before measurement, certain properties do not have definite values at all. This idea fundamentally alters how we think about physical reality. In the quantum world, particles are described by a mathematical object known as a wave function. The wave function does not tell us exactly where a particle is or what it is doing. Instead, it encodes probabilities. It tells us the likelihood of finding a particle in a particular place or state when a measurement is made. Until that measurement occurs, the particle cannot be said to possess a single, definite set of properties. Reality, at this level, exists as a range of possibilities rather than fixed facts. This probabilistic framework reaches one of its most profound expressions in the phenomenon of quantum tunneling. Classical intuition tells us that if an object does not have enough energy to overcome a barrier, it cannot pass through it. A ball thrown at a wall will bounce back if it lacks sufficient force to break through. Quantum mechanics defies this logic. Particles have a non-zero probability of passing through barriers, even when classical physics forbids it. Electrons can tunnel through energy barriers, appearing on the other side without ever having the required energy to cross them in a classical sense. This effect is not rare or hypothetical. It is essential to many natural processes and modern technologies, including nuclear fusion in stars and the operation of electronic components such as transistors. The existence of quantum tunneling reinforces the idea that probability governs the behavior of particles at fundamental scales. A particle does not need permission from classical rules to exist somewhere. It only needs a non-zero probability. This shift from certainty to probability reshapes the boundary between the possible and the impossible. In the quantum universe, events do not happen because they must. They happen because they can. Another area where quantum mechanics defies classical intuition is the concept of measurement itself. In classical physics, measurement is passive. Observing an object does not change its fundamental state. You can measure the temperature of water without altering its molecular structure. In quantum mechanics, measurement is active and intrusive. The act of observation changes the system being observed. When a measurement is made, the wave function collapses, and the system transitions from a superposition of possibilities to a single, definite outcome. This process is not fully understood, and it remains one of the most debated aspects of quantum theory. This measurement problem raises deep philosophical questions. Does reality exist independently of observation, or does observation play a role in bringing reality into being? While quantum mechanics does not require consciousness to function, it does demand interaction. Measurement involves an interaction between a quantum system and a measuring device, and this interaction forces the system into a particular state. The universe, at its core, appears to be relational rather than absolute, defined by interactions rather than isolated facts. The probabilistic nature of quantum mechanics also challenges the classical idea of trajectories. In everyday life, objects move along well-defined paths. A car travels from one location to another following a continuous trajectory. In the quantum world, particles do not follow precise paths in the classical sense. Instead, they explore all possible paths simultaneously. This idea is captured in the formulation of quantum mechanics known as the path integral approach, which suggests that particles take every possible route between 2 points, with probabilities assigned to each path. The observed behavior emerges from the combination of all these possibilities. This notion further erodes classical intuition. It suggests that nature does not choose a single path in advance, but allows all paths to contribute until an outcome is observed. Reality is not a single storyline unfolding deterministically. It is a vast collection of potential narratives, with probability determining which one becomes actualized. As experimental techniques advanced, the predictions of quantum mechanics were tested with increasing precision. Time and again, the probabilistic predictions of the theory matched experimental results with astonishing accuracy. Experiments involving single particles confirmed that outcomes could not be predicted individually, only statistically. When repeated many times, the results formed patterns that aligned perfectly with quantum probabilities. This statistical reliability, emerging from individual randomness, is one of the most remarkable features of quantum mechanics. It shows that order can arise from uncertainty, and predictability can coexist with chance. The success of quantum mechanics forced physicists to accept that classical intuition, shaped by humans, scale experiences, is not a reliable guide to the microscopic world. Our brains evolved to navigate a macroscopic environment where objects behave predictably and probabilities average out. At quantum scales, those averages no longer apply, and the raw probabilistic nature of reality becomes visible. What seems strange or illogical to us is simply the universe operating beyond the limits of our evolved intuition. This realization had a profound impact on Einstein and his contemporaries. Einstein accepted the mathematical success of quantum mechanics, but rejected the idea that probability was fundamental. He believed that the probabilistic outcomes reflected an incomplete theory, not an incomplete universe. In his view, there must be hidden variables, unknown factors, determining outcomes behind the scenes. Yet decades of experiments, including tests of Bell's inequalities, have shown that no local hidden, variable theory can reproduce the predictions of quantum mechanics. The universe appears to be genuinely probabilistic, not merely unknown. The implications of this conclusion are immense. It means that uncertainty is woven into the fabric of reality. The future is not entirely fixed, even in principle. While large-scale phenomena appear deterministic due to the averaging of countless quantum events, at the fundamental level, nature allows for multiple possible futures. This does not lead to chaos. Rather, it creates a structured uncertainty governed by precise mathematical laws. Quantum probability is not randomness without rules. It follows strict mathematical principles that enable extraordinary precision. The same probabilistic framework that prevents us from predicting the exact behavior of a single particle allows us to design technologies with remarkable reliability. Modern electronics, chemical reactions, and even biological processes rely on quantum probabilities. Life itself depends on quantum effects occurring within molecules and cells, quietly operating beneath our awareness. As researchers continue to explore quantum mechanics, the probabilistic nature of the theory is being harnessed in new and transformative ways. Quantum computers, for example, rely on superposition and probability to perform calculations that would be impossible for classical machines. Instead of processing information as fixed bits, quantum computers use quantum states that represent many possibilities at once. Computation becomes a guided exploration of probability space, exploiting uncertainty as a resource rather than a limitation. Quantum communication technologies also depend on probabilistic outcomes. Quantum cryptography uses the fundamental uncertainty of quantum measurement to ensure secure communication. Any attempt to intercept information inevitably disturbs the system, revealing the presence of an eavesdropper. In this way, the very feature of quantum mechanics that defies classical intuition becomes a powerful tool for protecting information. Ultimately, the first keynote that quantum mechanics defies classical intuition and introduces probabilistic outcomes is not just a technical statement. It represents a profound shift in humanity's understanding of reality. The universe is not a rigid machine unfolding with absolute certainty. It is a dynamic system of possibilities, where outcomes emerge through interaction, measurement, and probability. This view challenges our assumptions, humbles our expectations, and invites us to rethink what it means to know, predict, and understand the world. Quantum mechanics teaches us that reality is deeper and stranger than common sense allows, yet more elegant and consistent than chaos would suggest. By embracing probability rather than fearing it, physics has uncovered a richer and more accurate description of the universe, one that continues to reshape science, technology, and philosophy. In confronting the limits of classical intuition, quantum mechanics does not weaken our understanding. It expands it, revealing a universe where uncertainty is not a flaw, but a fundamental feature of existence. To understand why quantum entanglement troubled Albert Einstein so deeply, we must first understand how radically it contradicted everything he believed about the structure of reality. Einstein was not merely a physicist calculating equations. He was a thinker who believed that the universe must be logical, orderly, and independent of observation. His theories of relativity had reinforced this belief by presenting a universe governed by elegant, precise laws that respected causality and locality. In this world, no influence could travel faster than light, and objects could only be affected by their immediate surroundings. Entanglement shattered this picture. Quantum entanglement arises when two or more particles interact in such a way that their properties become linked, regardless of how far apart they later move. Once entangled, the state of one particle cannot be fully described without reference to the other. Measuring one instantly determines the state of its partner, even if the two are separated by vast distances. To Einstein, this appeared to violate the very foundation of physics, the idea that information or influence cannot travel faster than light. Einstein did not deny the mathematical predictions of quantum mechanics. He acknowledged that the equations worked remarkably well. What disturbed him was their interpretation. According to standard quantum theory, entangled particles do not possess definite properties until they are measured. Instead, they exist in a shared state of possibilities. When a measurement is made on one particle, the shared wave function collapses, instantly determining the outcome for the other particle. This instantaneous correlation seemed to suggest a form of communication faster than light, something Einstein believed was impossible. This led Einstein to famously describe entanglement as spooky action at a distance. The word spooky was not a casual remark. It reflected his deep discomfort. For Einstein, physics was meant to describe an objective reality that exists independently of observation. Entanglement seemed to imply that reality itself was non-local, that distant objects were mysteriously connected in ways that defied classical explanation. Einstein's objection was rooted in a principle known as locality. Locality asserts that an object can only be influenced by events occurring in its immediate vicinity. This principle is deeply embedded in both classical physics and relativity. If entanglement were truly instantaneous, it would appear to violate locality. Einstein found this unacceptable not only scientifically but philosophically. He believed that abandoning locality would undermine the rational structure of science itself. To challenge the prevailing interpretation of quantum mechanics, Einstein, along with Boris Podolsky and Nathan Rosen, formulated what is now known as the EPR paradox. Their goal was not to disprove quantum mechanics experimentally, but to show that it was incomplete. They argued that if quantum mechanics were correct as interpreted, then it would imply either instantaneous influences across space or the absence of an objective reality prior to measurement. Both possibilities were unacceptable to Einstein. The EPR argument proposed that entangled particles must carry hidden information, hidden variables, that determine their outcomes in advance. According to this view, measuring one particle does not instantaneously affect the other. It merely reveals information that was already there. The apparent spooky action would then be an illusion caused by our ignorance of these hidden variables. This interpretation would preserve locality and realism, two principles Einstein believed were essential. Einstein's insistence on hidden variables was not an act of denial, but an expression of his commitment to a deeper understanding of nature. He believed that quantum mechanics was a statistical approximation of a more complete theory, just as thermodynamics is a statistical description of molecular motion. In his view, probability should emerge from underlying certainty, not replace it. However, the philosophical divide between Einstein and proponents of quantum mechanics, particularly Niels Bohr, grew increasingly sharp. Bohr rejected the idea that quantum mechanics was incomplete. He argued that the very notion of objective properties existing prior to measurement was meaningless at the quantum level. According to Bohr, reality could not be separated from the act of observation. The question was not what properties a particle really has, but what can be said about it given a specific experimental setup. This debate was not merely academic. It exposed a fundamental conflict between two visions of reality. Einstein believed in a universe that exists independently of observers, governed by local, deterministic laws. Bohr embraced a universe where measurement plays a central role, and where uncertainty is fundamental. Entanglement stood at the heart of this conflict, symbolizing everything Einstein found troubling about quantum theory. What made entanglement especially unsettling was that it did not involve energy or matter traveling between particles. Instead, it involved relationships that appeared to exist outside classical space and time. Measuring one particle did not send a signal to the other, yet the outcome was instantly correlated. This subtlety made entanglement even harder to reconcile with classical intuition. It was not a force, not a wave, not a signal, yet its effects were undeniable. Einstein worried that accepting entanglement would lead physics down a path where explanation was replaced by description, where prediction was possible without understanding. He feared that physicists were becoming satisfied with mathematical success, while abandoning the search for underlying reality. For him, this represented a dangerous shift in the philosophy of science. Despite his objections, experimental evidence gradually accumulated in favor of entanglement. Advances in experimental techniques allowed physicists to test the predictions of quantum mechanics with unprecedented precision. These experiments consistently confirmed the existence of strong correlations between entangled particles, exactly as quantum theory predicted. Still, during Einstein's lifetime, there was no definitive experimental test that could rule out hidden variables completely. Einstein remained unconvinced until his death. He never accepted that nature was fundamentally non-local or probabilistic. Yet history would eventually show that the questions he raised were not misguided. On the contrary, they inspired some of the most important developments in modern physics. The effort to resolve the tension between quantum mechanics and Einstein's principles led to deeper insights into the structure of reality. Entanglement forced physicists to confront uncomfortable questions. Does reality exist independently of observation? Are distant objects truly separate, or are they part of a deeper, unified whole? Can the universe be both probabilistic and orderly? Einstein's struggle with entanglement was not a failure of imagination, but a refusal to accept answers that felt incomplete. Ironically, Einstein's skepticism helped strengthen quantum theory. By articulating its most troubling implications, he forced physicists to examine them more closely. The very phrase, "spooky action at a distance," captured the mystery so vividly that it became a lasting symbol of quantum strangeness. What Einstein intended as a critique became a powerful description of one of nature's most extraordinary features. In time, physicists would come to see entanglement not as a flaw in quantum mechanics, but as one of its most profound insights. It revealed that the universe is more interconnected than classical physics ever imagined. Space and distance, so central to Einstein's relativity, appeared less fundamental at the quantum level. Reality itself seemed to be woven from relationships rather than isolated objects. Thus, Einstein's struggle with entanglement represents one of the deepest intellectual confrontations in the history of science. It was a clash between intuition and evidence, between philosophical commitment and experimental success. While Einstein never accepted entanglement as fundamental, his resistance sharpened the questions that continue to drive physics today. As the decades passed after Einstein introduced the EPR argument, the question he raised became more urgent rather than fading away. Was quantum mechanics merely incomplete, as Einstein believed, or was nature itself fundamentally non-local and probabilistic? For a long time, this question remained philosophical rather than experimental. Physicists lacked a clear way to test whether hidden variables could explain entanglement while preserving locality. The debate lingered in textbooks, conferences, and private discussions, unresolved and deeply unsettling. This situation changed dramatically in the 1960s with the work of physicist John Bell. Bell transformed Einstein's philosophical objection into a precise mathematical framework. He derived what are now known as Bell's inequalities relationships that any local hidden variable theory must satisfy. Quantum mechanics, however, predicted violations of these inequalities under specific conditions. For the first time, Einstein's discomfort with entanglement could be tested experimentally. Nature itself would decide whether locality and hidden variables could survive. Bell's work was revolutionary because it clarified what was truly at stake. The question was no longer whether quantum mechanics felt strange or counterintuitive, but whether the universe could be both local and realistic at the same time. If experiments violated Bell's inequalities, then no theory based on local hidden variables could explain reality. Einstein's hope for a deeper, deterministic layer beneath quantum mechanics would be shattered. When experiments were eventually performed, the results were unambiguous. Starting in the 1970s and refined over the following decades, increasingly sophisticated experiments tested entangled particles under controlled conditions. Again and again, the predictions of quantum mechanics were confirmed. Bell's inequalities were violated exactly as quantum theory predicted. No local hidden, variable explanation could account for the observed correlations. These results were devastating to Einstein's position, though he did not live to see their full confirmation. The universe appeared to be non-local in a fundamental sense. Entangled particles behaved as parts of a single system, even when separated by large distances. Measurement outcomes were correlated in ways that could not be explained by pre-existing properties or classical communication. The spooky action Einstein feared was not an illusion. It was a real feature of nature. Yet, this non-locality did not mean that information was traveling faster than light in a usable way. This distinction is crucial. Although entanglement creates instantaneous correlations, it does not allow for faster than light signaling. One observer cannot use entanglement alone to send a message to another observer. Relativity remains intact, even as classical intuition is challenged. The universe respects the speed limit of light while still allowing deeply non-classical connections. This subtle balance between non-local correlations and relativistic constraints illustrates the depth of Einstein's struggle. His theory of relativity remains one of the most successful descriptions of space and time ever developed. Yet quantum entanglement reveals that space and time are not the whole story. At the quantum level, reality appears to be structured in a way that transcends classical separations. Distance becomes less fundamental than correlation. As physicists came to accept entanglement as a real phenomenon, their interpretation of it evolved. What once seemed like a flaw in quantum mechanics began to look like one of its most powerful insights. Entanglement suggested that the universe is not composed of independent building blocks, but of interconnected systems. Particles do not merely exist side by side, they exist in relationships. These relationships persist even when the particles are separated by space. This relational view of reality has profound implications. It suggests that separateness is, to some extent, an illusion, a macroscopic approximation that breaks down at fundamental scales. While everyday objects appear independent, their underlying constituents are governed by laws that allow deep, non-local connections. Einstein's discomfort arose precisely because this view conflicted with the clear geometric structure of space-time that his own theories described so successfully. Ironically, entanglement has become one of the most experimentally verified and technologically valuable aspects of quantum mechanics. Modern laboratories routinely create and manipulate entangled states with extraordinary precision. What Einstein once regarded as a sign of incompleteness is now treated as a resource. Quantum technologies actively rely on entanglement to perform tasks that are impossible within classical frameworks. Quantum cryptography, for example, uses entanglement to guarantee security. Because measuring an entangled particle inevitably disturbs its state, any attempt at interception is immediately detectable. This security does not depend on computational difficulty, but on the fundamental laws of physics. In this sense, entanglement turns uncertainty into protection. Quantum computing also depends on entanglement. By linking quantum bits into entangled states, quantum computers can explore vast spaces of possibilities simultaneously. This allows certain problems to be solved far more efficiently than any classical machine could manage. The same phenomenon Einstein distrusted now lies at the heart of some of the most advanced technologies humanity has ever conceived. Despite these successes, the philosophical questions Einstein raised have not disappeared. Even today, physicists and philosophers debate the meaning of entanglement. Does it imply that reality is fundamentally holistic? Does it require us to abandon classical notions of objectivity? Or does it point toward an even deeper theory that has yet to be discovered? While experiments have ruled out local hidden variables, they have not eliminated all possible interpretations of quantum mechanics. Some interpretations accept non-locality as fundamental. Others suggest that all possible outcomes exist simultaneously, branching into different realities. Still, others attempt to preserve determinism by allowing non-local hidden variables. What unites these efforts is a shared recognition that Einstein's concerns were legitimate. Entanglement forces us to confront the limits of classical reasoning and to rethink what we mean by explanation. Einstein's resistance to entanglement was not rooted in ignorance or stubbornness. It was rooted in his deep commitment to clarity, causality, and realism. He believed that physics should describe a world that exists independently of our measurements. Entanglement challenged this belief by making measurement central to the definition of physical properties. In doing so, it blurred the line between observer and system in a way Einstein found unacceptable. Yet history has shown that discomfort is often a sign of progress in science. When a theory challenges intuition, it forces us to refine our understanding. Entanglement did not destroy Einstein's legacy, it enriched it. His questions sharpened the theory, motivated crucial experiments, and helped define the foundations of modern physics. Without his objections, quantum mechanics might have remained mathematically successful, but conceptually shallow. Today, entanglement is no longer seen as spooky, in a negative sense, but as a window into the deep structure of reality. It suggests that the universe is not merely a collection of things moving through space and time, but a network of correlations that define what can happen and what can be known. Space, time itself may emerge from these deeper quantum connections, rather than serving as their stage. In this light, Einstein's struggle takes on a new meaning. He was not wrong to resist easy answers. He was wrong only in believing that locality and realism must be preserved at all costs. Nature, it seems, is under no obligation to align with human intuition. Instead, it reveals its truths through experiment, even when those truths are unsettling. The story of entanglement is therefore not a story of Einstein's failure, but of his intellectual courage. He dared to challenge a theory that worked because he believed understanding mattered more than calculation. In the end, the universe answered his challenge, not by restoring classical order, but by revealing a deeper, stranger, and more interconnected reality than anyone had imagined. The debate over determinism versus probability in the universe lies at the very heart of modern physics and philosophy. It asks a simple yet profound question: is everything that happens in the universe completely determined by prior causes, or does chance play a fundamental role in how reality unfolds? For centuries, scientists believed firmly in determinism, the idea that if we knew all the laws of nature and the exact state of the universe at one moment, the future could be predicted with perfect accuracy. This belief shaped classical physics and human understanding of nature until the rise of quantum mechanics forced a dramatic rethinking. Determinism found its strongest expression in classical physics, especially in the work of Isaac Newton. In the Newtonian universe, objects move according to precise laws of motion. If you know the forces acting on an object and its initial position and velocity, its future behavior can be calculated exactly. This led to the vision of the universe as a vast, perfectly ordered machine. Every event was the inevitable result of previous events, leaving no room for true randomness. Uncertainty, in this view, came only from ignorance. If predictions failed, it was because we lacked sufficient information, not because nature itself was uncertain. This deterministic world view extended beyond physics into philosophy and everyday thinking. It suggested that the universe follows a fixed script, where cause and effect govern everything from planetary motion to human actions. Many thinkers found comfort in this order, believing that nature must be rational, predictable, and ultimately understandable through reason. Even Albert Einstein, despite revolutionizing physics with relativity, remained deeply committed to determinism. His theories described space and time with mathematical precision, and preserved the idea that physical laws operate consistently across the universe. The arrival of quantum mechanics in the early 20th century shattered this certainty. Experiments at atomic and subatomic scales revealed behavior that could not be explained by deterministic laws. Instead of producing single, definite outcomes, quantum systems yielded results that could only be predicted probabilistically. For example, quantum theory cannot predict exactly when a radioactive atom will decay. It can only give the probability that decay will occur within a certain time. This randomness is not due to incomplete knowledge. It appears to be built into the fabric of reality itself. At the center of this shift is the quantum wave function, which describes all possible states a system can occupy. Rather than assigning definite properties to particles, the wave function assigns probabilities. When a measurement is made, one outcome occurs, but which one happens cannot be predicted with certainty. This marks a radical departure from classical thinking. Probability in quantum mechanics is not a temporary placeholder for missing information. It is a fundamental feature of how nature operates. This idea deeply disturbed Einstein and others who believed the universe must be governed by underlying certainty. Einstein famously objected to quantum randomness, insisting that God does not play dice with the universe. He believed that quantum mechanics was incomplete and that hidden variables, unknown factors beneath the surface, must determine outcomes in a deterministic way. According to this view, probability merely reflected our lack of knowledge, not true randomness in nature. However, decades of experimental work have challenged Einstein's hope for a deterministic foundation. Tests of quantum entanglement and Bell's inequalities have shown that no local hidden variable theory can reproduce the predictions of quantum mechanics. These experiments strongly suggest that the probabilistic nature of quantum outcomes is not due to missing information, but is genuinely fundamental. The universe, at its deepest level, does not appear to follow a fixed script. This realization has profound implications for how we understand reality. If probability is fundamental, then the future is not completely determined by the past. Multiple outcomes are genuinely possible, and which one occurs is not fixed in advance. This does not mean the universe is chaotic or lawless. Quantum mechanics is governed by precise mathematical rules, but these rules determine probabilities rather than certainties. Order still exists, but it is an order based on likelihood rather than inevitability. The debate between determinism and probability also raises important philosophical questions. What does it mean to explain something if we can only give probabilities rather than causes? Is a probabilistic explanation less satisfying than a deterministic one? For some, randomness seems to undermine the idea of a rational universe. For others, it reflects a deeper and more subtle kind of order, one that allows flexibility, creativity, and novelty within natural law. Interestingly, probability at the quantum level does not conflict with the apparent determinism of everyday life. At large scales, the random behavior of countless particles averages out, producing stable and predictable patterns. This is why classical physics works so well for everyday objects, even though it breaks down at microscopic scales. Determinism, in this sense, emerges from probability rather than replacing it. The macroscopic world appears deterministic not because randomness is absent, but because it becomes statistically insignificant. Modern physics increasingly views determinism and probability not as absolute opposites, but as complementary aspects of reality. The laws governing quantum systems are strict and precise, yet their outcomes are probabilistic. This combination challenges our intuition, but has proven extraordinarily successful in explaining and predicting natural phenomena. Technologies such as semiconductors, lasers, and quantum computing all rely on this probabilistic framework. Ultimately, the debate over determinism versus probability reflects a deeper human struggle to understand control, predictability, and meaning in the universe. Determinism offers certainty and order, while probability introduces openness and uncertainty. Quantum mechanics suggests that the universe contains both structure and freedom, law and chance. Rather than being a weakness, This balance may be one of nature's most profound strengths. In accepting probability as fundamental, science does not abandon reason, it expands it. The universe may not be fully predictable, but it remains deeply intelligible. By embracing uncertainty, modern physics has revealed a richer, more complex picture of reality, one in which the future is shaped not by necessity alone, but by possibility itself. Einstein's insistence on hidden variables to restore predictability was rooted in his deep philosophical commitment to a rational, orderly universe. For him, the success of physics had always depended on the idea that nature follows precise laws, and that apparent randomness reflects human ignorance rather than fundamental disorder. When quantum mechanics emerged with its probabilistic predictions, Einstein accepted its mathematical power, but rejected the idea that chance was an irreducible feature of reality. He believed that beneath quantum uncertainty there must exist hidden variables, unknown elements of reality that determine outcomes in a precise and predictable way. In classical physics, probability arises only when information is incomplete. A coin toss appears random because we cannot track every force and motion involved. But in principle, if all variables were known, the outcome would be fully determined. Einstein believed the same must be true for quantum phenomena. When quantum mechanics predicted probabilities instead of certainties, he saw this not as a final description of nature, but as evidence of an incomplete theory. In his view, the wave function did not describe reality itself. It described our limited knowledge of an underlying, more complete state of the system. This belief was closely tied to Einstein's commitment to realism, the idea that physical properties exist independently of observation. Quantum mechanics, especially in its standard interpretation, suggested that particles do not have definite properties until they are measured. For Einstein, this was unacceptable. He argued that the moon does not cease to exist when no one looks at it, and likewise, particles must possess definite attributes whether or not they are observed. Hidden variables offered a way to preserve this realism by assigning concrete properties to particles at all times. Einstein was also deeply concerned about locality, a principle reinforced by his theory of relativity. Locality holds that objects can only be influenced by their immediate surroundings, and that no influence can travel faster than light. Quantum entanglement appeared to violate this principle by allowing distant particles to display instant correlations. Einstein believed that hidden variables could resolve this problem by explaining these correlations without invoking faster than light influences. If the outcomes were predetermined by shared hidden information, then no mysterious action at a distance would be required. These concerns came together in the famous Einstein-Podolsky-Rosen argument. In this thought experiment, Einstein and his collaborators aimed to show that quantum mechanics could not be a complete description of reality. They argued that if quantum predictions were correct, then either locality or realism had to be abandoned. Rather than accepting this conclusion, Einstein insisted that the theory must be missing something. Hidden variables, he believed, would restore both locality and determinism, preserving the logical structure of physics. Einstein did not propose a detailed hidden, variable theory himself. His focus was on principle rather than construction. He was convinced that future developments in physics would reveal a deeper layer beneath quantum mechanics, just as classical thermodynamics had eventually been explained by molecular theory. In this deeper theory, probabilities would emerge from ignorance of precise details, not from intrinsic randomness. However, Einstein's hope faced increasing challenges as quantum mechanics continued to succeed experimentally. Every test confirmed its probabilistic predictions with remarkable accuracy. Still, Einstein remained unconvinced, believing that empirical success did not guarantee conceptual completeness. He often warned against confusing predictive power with understanding, arguing that physics should aim not only to predict outcomes, but to explain why they occur. After Einstein's time, physicists began to examine hidden, variable theories more rigorously. The most significant breakthrough came with John Bell's work, which showed that no local hidden, variable theory could reproduce all the predictions of quantum mechanics. Experiments testing Bell's inequalities repeatedly confirmed quantum predictions, suggesting that Einstein's vision of restoring predictability through local hidden variables was not compatible with nature as we observe it. Despite this, Einstein's insistence on hidden variables was not a mistake or a failure. It played a crucial role in sharpening the foundations of quantum theory. By clearly articulating what he found unacceptable, Einstein forced physicists to confront the philosophical implications of quantum mechanics. His objections led to deeper insights into non-locality, entanglement, and the limits of classical reasoning. Even today, the idea of hidden variables has not entirely disappeared. Some modern interpretations of quantum mechanics explore non-local hidden, variable theories that preserve determinism at the cost of locality. Others continue to search for deeper frameworks that might reconcile quantum mechanics with gravity. In this sense, Einstein's insistence remains influential, guiding ongoing efforts to understand the universe at its most fundamental level. Ultimately, Einstein's pursuit of hidden variables reflects his unwavering belief that nature must be comprehensible and logically coherent. While the universe may not conform to his expectations of determinism, his challenge pushed physics to greater clarity and depth. His resistance to accepting randomness as fundamental was not a refusal to progress, but a demand for deeper explanation. In questioning quantum mechanics so relentlessly, Einstein ensured that its strange implications were taken seriously, transforming uncertainty from a weakness into one of the most profound insights of modern science. The philosophical clash between Albert Einstein and Niels Bohr over the interpretation of quantum mechanics is one of the most profound intellectual debates in the history of science. It was not merely a disagreement over equations or experiments, but a deep conflict about the nature of reality, knowledge, and what science itself is meant to describe. At its core, this clash represented two radically different visions of the universe, one grounded in certainty, objectivity, and realism, and the other embracing uncertainty, probability, and the limits of what can be known. Albert Einstein believed that the goal of physics was to describe an objective reality that exists independently of observation. For him, physical properties such as position, momentum, and energy were real attributes of objects, whether or not anyone measured them. This belief was rooted in the success of classical physics and reinforced by his own theories of relativity, which depicted a universe governed by precise, deterministic laws. Einstein was willing to accept revolutionary ideas, but he insisted that nature must ultimately be rational, orderly, and intelligible. Randomness, in his view, could only reflect incomplete knowledge, not a fundamental feature of reality. Niels Bohr, on the other hand, held a very different perspective. As one of the principal architects of quantum mechanics, Bohr argued that classical concepts simply do not apply at the atomic scale. According to his interpretation, known as the Copenhagen interpretation, quantum systems do not possess definite properties until they are measured. The act of measurement is not a passive observation of pre-existing reality, but an active process that plays a crucial role in determining outcomes. For Bohr, asking what a particle really is before measurement was not a meaningful scientific question. This difference in outlook led to a fundamental disagreement over the meaning of the quantum wave function. Einstein saw the wave function as a tool for calculating probabilities, not as a complete description of reality. He believed that it must be supplemented by additional variables that would restore determinism and objectivity. Bohr, by contrast, regarded the wave function as a complete description of what can be known about a system. He argued that quantum mechanics does not describe an underlying reality independent of observation, but rather the outcomes of interactions between systems and measuring devices. Their clash became most famous during a series of debates at scientific conferences, particularly the Solvay conferences in the 1920s and 1930s. Einstein repeatedly presented thought experiments designed to expose what he believed were inconsistencies or absurdities in Bohr's interpretation. He aimed to show that quantum mechanics either violated causality or allowed for physical properties to exist without clear definition. Each time, Bohr responded by carefully analyzing the experimental setup and demonstrating that Einstein's conclusions relied on applying classical reasoning where it no longer applied. One of the central points of contention was determinism versus probability. Einstein could not accept that the universe operates fundamentally by chance. His famous remark, "God does not play dice with the universe," captured his discomfort with quantum randomness. Bohr replied that it was not the role of physicists to tell nature how it should behave. For Bohr, probability was not a temporary flaw in the theory, but an essential feature of the quantum world. He believed that quantum mechanics had revealed a limit to what humans can know, not a failure of physical law. Another major disagreement concerned realism and locality. Einstein insisted that physical systems must have definite properties and that influences cannot travel faster than light. Quantum mechanics, especially through phenomena like entanglement, seemed to violate both principles. Bohr responded by redefining the problem. He argued that quantum properties are not attributes of isolated particles, but of entire experimental arrangements. In this view, questions about distant particles influencing each other miss the point, because quantum mechanics does not describe independent objects in the classical sense. Bohr introduced the principle of complementarity to explain this new way of thinking. According to this principle, certain properties, such as wave, like and particle, like behavior, are mutually exclusive yet both necessary for a complete description of quantum phenomena. Which property appears depends on the experimental context. Einstein found this deeply unsatisfying. To him, complementarity seemed to abandon the idea that physics should describe what exists, replacing it with a focus on what can be measured. Despite their intense disagreements, the relationship between Einstein and Bohr was marked by mutual respect. Bohr admired Einstein's genius and took his criticisms very seriously. Einstein, in turn, respected Bohr's intellectual honesty, even as he rejected his conclusions. Their debate was not about winning arguments, but about clarifying the foundations of science. Each forced the other to sharpen their ideas, leading to a deeper understanding of quantum mechanics. Over time, experimental evidence increasingly supported Bohr's interpretation. Tests of quantum entanglement and related phenomena confirmed predictions that aligned with the Copenhagen view and challenged Einstein's hopes for a deterministic, local explanation. While Einstein never accepted these results as the final word, the scientific community gradually embraced the probabilistic and non-classical nature of quantum theory. Yet, the philosophical issues raised by Einstein have never fully disappeared. Questions about realism, determinism, and the role of the observer continue to be debated today. Modern interpretations of quantum mechanics reflect this ongoing struggle to reconcile mathematical success with conceptual clarity. In this sense, Einstein's objections remain as relevant as Bohr's answers. The clash between Einstein and Bohr represents more than a disagreement between two great scientists. It marks a turning point in humanity's understanding of reality. Einstein stood for a universe that exists independently and predictably, while Bohr accepted a universe where knowledge is limited and context-dependent. Their debate reshaped physics by revealing that nature does not always conform to human intuition. Ultimately, this philosophical clash taught science an enduring lesson. Progress often comes not from agreement, but from deep, principled disagreement. By challenging each other at the highest intellectual level, Einstein and Bohr expanded the boundaries of human understanding. Their debate continues to inspire physicists and philosophers alike, reminding us that the quest to understand reality is as much about questioning our assumptions as it is about discovering new facts. Modern experiments confirming entanglement and validating quantum predictions represent one of the most decisive chapters in the history of science. What once appeared as a philosophical puzzle or a troubling implication of theory has now become an experimentally verified feature of reality. Over the past several decades, physicists have moved entanglement from the realm of thought experiments into the laboratory, demonstrating again and again that quantum mechanics accurately described the behavior of nature at its most fundamental level. For a long time, entanglement existed mainly as a theoretical consequence of quantum mechanics. While the mathematics was clear, many physicists, including Einstein, wondered whether its strange implications reflected real physical connections or merely incomplete knowledge. Early quantum experiments confirmed probabilistic predictions, but they were not sufficient to settle deeper questions about locality and hidden variables. The challenge was to design experiments that could directly test whether entangled particles behave in ways that no classical explanation could reproduce. This challenge was met through increasingly precise tests inspired by Bell's theorem. Bell showed that if the world obeyed classical ideas of locality and predetermined properties, then certain statistical limits, known as Bell's inequalities, could never be exceeded. Quantum mechanics, however, predicted that entangled particles would violate these limits. Modern experiments were designed to test this prediction under controlled conditions, using pairs of particles whose properties could be measured independently at large distances. Beginning in the late 20th century, experimental groups used photons, electrons, and other particles to test Bell's inequalities. These experiments consistently showed violations exactly where quantum mechanics predicted them. The correlations between entangled particles were stronger than any local hidden variable theory could allow. This result was not occasional or ambiguous. It was robust, repeatable, and increasingly precise as experimental techniques improved. One of the most important developments was the ability to create and control entangled particles with high reliability. Advances in lasers, detectors, and timing systems allowed physicists to measure entangled states with extraordinary accuracy. Researchers ensured that measurements were made far enough apart and fast enough to prevent any classical communication between detectors. Even under these strict conditions, quantum correlations persisted, confirming that entanglement is not an artifact of experimental error or incomplete isolation. Over time, scientists addressed potential loopholes that critics raised. Some argued that earlier experiments left open the possibility of hidden influences or biased sampling. In response, researchers designed loophole-free experiments that closed these gaps simultaneously. These experiments left no reasonable classical explanation for the observed correlations. The results strongly supported the conclusion that entanglement is a genuine feature of nature, not a mathematical illusion. Beyond testing Bell's inequalities, modern experiments have confirmed other quantum predictions related to entanglement. Scientists have demonstrated quantum teleportation, where the quantum state of one particle is transferred to another distant particle without physically sending the particle itself. This process relies entirely on entanglement and would be impossible under classical physics. While no matter or usable information travels faster than light, the successful transfer of quantum states provides striking confirmation of quantum theory's accuracy. Experiments have also shown that entanglement can persist over surprisingly large distances. Entangled photons have been transmitted across kilometers of optical fiber and even between ground stations and satellites. These achievements demonstrate that quantum correlations are not fragile, theoretical constructs, but stable physical phenomena that can survive real-world conditions. The fact that entanglement remains intact across such distances further validates the predictions of quantum mechanics. Importantly, these experimental confirmations have practical consequences. Quantum cryptography uses entanglement to guarantee secure communication. Any attempt to intercept or measure entangled particles disrupts their correlations, immediately revealing interference. This security is not based on assumptions about computational difficulty, but on the fundamental laws of physics. The success of quantum communication systems in laboratory and field tests reinforces confidence in quantum theory's predictions. Quantum computing also relies heavily on entanglement. Experiments have demonstrated that entangled quantum bits can perform coordinated operations that have no classical equivalent. While large-scale quantum computers are still under development, existing experimental devices already show behavior that aligns precisely with quantum predictions. These results further confirm that quantum mechanics is not only correct, but technologically exploitable. What makes these modern experiments especially significant is that they go beyond confirming numerical predictions. They validate the conceptual framework of quantum mechanics itself. The experiments show that the universe allows non-classical correlations that cannot be explained by pre-existing properties or local causes alone. Nature behaves in accordance with quantum probability, even when this behavior defies classical intuition. At the same time, these results do not overturn Einstein's theory of relativity. Although entanglement involves instantaneous correlations, it does not allow faster than light communication. Experiments confirm that quantum mechanics respects relativistic constraints while still exhibiting non-local features. This delicate balance highlights the internal consistency of modern physics, even as it challenges traditional notions of space and causality. The confirmation of entanglement has also reshaped philosophical thinking about reality. It suggests that the universe is fundamentally interconnected, with relationships playing a more central role than individual objects. Physical properties do not always belong to isolated particles, but can be shared across systems. This idea marks a profound shift from classical thinking and reflects a deeper understanding of how nature operates. Einstein's riddle inspires ongoing exploration into the fundamental nature of reality because it touches the deepest questions science can ask. What is real? How does the universe truly work? And are there limits to human understanding? Although Einstein's objections to quantum mechanics did not overturn the theory, they revealed unresolved tensions at the heart of modern physics. These tensions continue to motivate research today, driving scientists to probe beyond established frameworks in search of a deeper and more unified description of nature. Einstein's riddle emerged from his refusal to accept that the universe is fundamentally probabilistic and non-local. He believed that the extraordinary success of quantum mechanics masked an incomplete understanding of reality. In his view, the theory described observations accurately, but failed to explain what was actually happening behind the scenes. This insistence on deeper explanation set a powerful standard for scientific inquiry. Rather than settling for predictive success alone, Einstein demanded conceptual clarity, and this demand remains central to ongoing research in theoretical physics. One of the most significant ways Einstein's riddle continues to inspire exploration is in the search for a deeper theory that unifies quantum mechanics with gravity. Quantum theory governs the microscopic world, while general relativity describes space, time, and gravity at cosmic scales. Despite their individual successes, these two pillars of modern physics are fundamentally incompatible. The latter part of his Sino de Life, and modern physicists continue this quest. The unresolved tension between quantum non-locality and the geometric structure of space-time suggests that our current understanding is incomplete. Research into quantum gravity reflects this influence directly. Approaches such as loop quantum gravity and string theory attempt to describe space, time itself as emerging from more fundamental quantum structures. These efforts echo Einstein's intuition that space and time might not be fundamental, but derived from deeper principles. The strange features of entanglement, which troubled Einstein, are now seen as potential clues to the true nature of space-time, suggesting that geometry may arise from quantum correlations. Einstein's riddle also fuels ongoing debates about the interpretation of quantum mechanics. Although the mathematical formalism is well established, there is still no universal agreement on what the theory means. Different interpretations offer radically different views of reality, ranging from universes branching into multiple outcomes to hidden structures guiding quantum behavior. The persistence of these debates reflects Einstein's lasting influence. His insistence that understanding matters has prevented physicists from treating interpretation as a purely philosophical distraction. Experimental research continues to push the boundaries of quantum mechanics, inspired by the same questions Einstein raised. Scientists now test quantum effects in increasingly complex and macroscopic systems, exploring where the boundary between quantum and classical behavior lies. Experiments involving large molecules, superconducting circuits, and mechanical systems aim to determine whether quantum principles apply universally or break down at certain scales. Each new test probes the limits of quantum theory and addresses the question of whether it is truly complete. Einstein's riddle also plays a role in the study of quantum information. The realization that entanglement is a fundamental resource has transformed how physicists think about information, computation, and reality itself. Information is no longer viewed as merely something stored in physical systems, but as a foundational aspect of physical law. This shift aligns with Einstein's belief that understanding reality requires uncovering its most basic principles, even if those principles differ from classical expectations. The philosophical impact of Einstein's riddle extends beyond physics. It challenges long-held assumptions about determinism, causality, and objectivity. If reality is not fully determined until measurement, what does that mean for the nature of existence? If distant systems are fundamentally connected, what does that imply about separateness and individuality? These questions influence philosophy of science, metaphysics, and even discussions about consciousness, showing how Einstein's concerns continue to shape broader intellectual inquiry. Importantly, Einstein's riddle teaches an enduring lesson about scientific progress. It demonstrates that disagreement and skepticism are not obstacles to discovery but essential drivers of it. Einstein's refusal to accept quantum mechanics uncritically did not hinder physics. It strengthened it. By articulating the deepest problems in the theory, he forced physicists to refine their ideas, design better experiments, and clarify what the theory truly implies about the universe. Even today, physicists do not claim to have final answers. While quantum mechanics works extraordinarily well, many believe it is not the ultimate description of reality. Questions about the nature of time, the origin of the universe, and the meaning of quantum probabilities remain open. Einstein's riddle continues to inspire the belief that beneath current theories lies a deeper level of understanding waiting to be discovered. In this sense, Einstein's legacy is not defined by the answers he accepted, but by the questions he refused to abandon. His riddle serves as a reminder that science advances not only through solutions, but through persistent inquiry. By challenging assumptions and demanding coherence, Einstein shaped a scientific culture that values depth over comfort. Ultimately, Einstein's riddle endures because it speaks to the human desire to understand the universe at its most fundamental level. It encourages scientists to look beyond successful formulas and ask what reality truly is. Whether future discoveries confirm or overturn current theories, the spirit of Einstein's challenge will remain at the heart of scientific exploration, guiding the quest to uncover the deepest structure of existence.